Hey Geometry, welcome to section 10.7. We're going to look in this section at special segments in circles. And so we're going to look at chords and secants and things like that. So when two chords intersect inside a circle, each chord is divided into two segments called chord segments. If two chords intersect in a circle, then the products of the length of the chord segments are equal. So this is kind of a weird property, equal. I don't know where that R came from, sorry. Equal. So for example, in this case, we've got some chords intersecting, and we know that those parts will be equal. So if I do like AB times BC, that's going to end up being EB times BD. Let me show you real quickly why that is. It's a weird property to see. But it comes from congruent triangles. And so if you ever forget this, just try and break things down into congruent triangles. So I'm going to draw in some triangles here. Sorry, not congruent, similar triangles. And so we know that, for instance, in this case, that angle C and E, as I've drawn them, both intercept the same arc. So we know those would actually be congruent. They're both half of whatever that arc measure is. And then like A and D both intercept the same arc as well. So they're congruent. And finally, we have vertical angles. So we have similar triangles that we could create that way. And then once we have that, we could set up sides are proportional. So for instance, like AB, we could set, let me try and get this set up right. So I'm going to say AB over BD. Those sides are proportional. And then EB over BC, or sorry, yeah, am I doing that right? AB over BD is equal to EB over BC. And so then if we cross multiply, what do we get? That right there, AB times BC is equal to EB times BD, or BD times EB, same thing. And so you can get it from this idea. But it can be really convenient, just go straight to, these things got to multiply. So in this case, those chord segments multiply. AB is 5 times BC is 12. So 5 times 12 is equal to X times 10. And solve away, we get 60 is equal to 10x, so x is 6 for that one. Here, a little bit trickier, a bunch of x's going on here, so I can say x plus 10 times x, so I actually need to get that in parentheses, is equal to x plus 1 times x plus 8. All right, and this one we got a little more work for us in the algebra. So distributive property here, so we get x squared plus 10x is equal to, and then foiling these together, x squared outside is 8x, inside is 1x, so I'm going to go ahead and combine that to 9x, and then last is 8. Nicely though, we can do the thing where we cancel off minus x squared on both sides, so that's going to go away. And I'm going to go ahead and bring x's to the left at this point, so minus 9x, so that's gone. I'm left with x on the left and 8 on the right. Actually kind of cleaned up quicker than expected. All right, so in this one, the true shape of a rainbow is a complete semicircle. However, we see only the arc of the circle that appears above the Earth's horizon. What is the radius of the circle containing the arc of the rainbow shown? All right, so for this one, I wanted to draw it in here a little bit more. In theory, this circle continues on down below, but we can kind of break this up and use this property to help us with this. We got 0.7 miles here. We got a 5-mile chord there, but that would be split into 2.5 and 2.5 for the horizon going across there. And so that what we want to figure out is, I'll first figure out what this length is that goes all the way to, it really is outside the circle down here somewhere. Figure out what x is, and then once I know that, I can figure out the diameter and then get the radius of that rainbow. So we can set up a 2.5 times 2.5 is equal to 0.7 times x, 0.7, and then x would be the rest of it. Because the diameter is a chord, so we're ultimately 0.7 and x combined to be the diameter. So 2.5 times 2.5 is 6.25. That is equal to 0.7x. We divide both sides by 0.7. We get that x is 8.9 approximately. So if I divide both sides by 0.7, divide by 0.7. And so that's 8.9. And so that means my diameter is 8.9. I'm going to go ahead and say D. Diameter is 8.9 plus 0.7, which is 9.6. And then our radius is going to be half that, 9.6 over 2. And so we get 4.8. And the units on this are miles. So a 4.8 mile radius for that rainbow. All right, so on the back here, we have another type of segment. These are secant segments. So a secant segment is a segment of a secant line that has exactly one endpoint on the circle. So AC is a secant line. So, a secant segment would end at that point. A secant line goes through the circle. It's not a tangent line. It's a secant line, one that crosses the circle and has 2 points. But a secant segment ends on the circle. So, for instance, in this case, AC is a secant segment, and AB ends on the circle, and AE and AD, those are all considered secant segments. A secant segment that lies in the exterior of the circle is called an external secant segment. So in the figure, both AB and AD are external secant segments. And so there's a special relationship, and this comes from similar triangles again, that we can come up with secant segments. So if two secants intersect in the exterior of a circle, like these, then the product, so we're going to multiply, of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secants and its external secant segment. So in this case, we could do AC times AB, that's its external secant segment, and AE times AD. And again, we could go through a thing where we show why this works. It's proportional. We can actually kind of show that these triangles here, if we drew those in, we could show that those are similar triangles. Again, like angle A and these two are the same, and then we have vertical angles, and actually that's enough to show that those two angles are similar, and so we can set up ratios and show that, but we'll just leave it at there. If you want to explore that more, you can. So use the intersection of these two, so these should be secants. So what we can do is we can find x. We need the full length times the external length. So this would be x plus 8 times just the 8 part. And then on the other side, we can do 10 plus 6. So I'm going to go ahead and just call that 16 times, and then the external part. So the full secant segment and then the external secant segment. So all the way to the other side and so on. So if we then do some multiplication and some distributive, we get 8x plus 64 is equal to 6 times 16 is 96. And so we can subtract 64 from both sides. 8x this ends up being 32. If we divide by divide both sides by 8, we get x is 4. And we can solve for x in that case. An equation similar to the secant segment theorem can be used when the secant and a tangent intersect outside the circle. In this case, the tangent segment or segment of a tangent with one endpoint on the circle is both the exterior and the whole segment. So we can treat this like it's a secant, even though it's really a tangent, and say that that's the whole and the exterior. So the way that works is if a tangent and a secant segment intersect in the exterior of a circle, then the square of the measures of the tangent is equal to the product of the measures of the secant and its external secant segment. So in this case, it would be like JK, or so it's like JM times LJ would be equal to KJ times KJ. And so where we actually get is KJ squared is equal to, well, that should not say AE, sorry, this should say JM times JL, those two parts. So applying this, use the intersection of the secant and the tangent. PQ is tangent to the circle, find X, and we're going to round to the nearest tenth. And so we'll do PQ times PQ, so we'll just do 8 squared, is equal to this full length, which is X plus 7, times the external part, which is just X. And so we end up here with quadratic, because this ends up being X squared plus 7x is equal to 8 squared is 64. And so in this case, we can try and solve this a couple ways. Usually we set it equal to 0. So I'm going to bring the 64 over. So I'm going to say 0 is equal to x squared plus 7x plus 64. So we got our old classic quadratic to solve from algebra. We might try and think through, are there a couple of nice numbers that multiply to be 64 and then add to be 7, so we can do the factoring thing and find the answers? You can try it for a while if you want. It's not going to work out. And maybe a hint here is that it does say to the nearest tenth. This isn't going to end up being nice answers. So instead, we might go to our quadratic formula, which is the negative b plus or minus b squared. So we can say, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And so in this case, a is 1, b is 7, and c is 64. And we'll plug all that in. So it's going to be negative 64, or sorry, not 64, negative b, so negative 7, plus or minus the square root of b squared, 7 squared, minus 4 times a, which is a 1, times c, which is 64, all over 2a, so 2 times 1. And so if we punch this stuff into our calculator, we get negative 7 plus and minus. This ends up being the square root of 7 squared minus 4 times 64. What am I doing wrong here? There's something I messed up. So I say this should not be negative. If I'm trying to take a square root of a negative, I get an imaginary number, and this should be a real number. So if I look back, I had 64 on the left here, and when I brought it to the right side, I forgot to subtract it. So that actually should have been minus 64, which makes this negative 64. So C is negative 64. If we get that in there, that's going to clean this up. So it's 7 squared minus and then it's 4 times 1 times negative 64, which is going to end up making that minus positive, and so that ends up being 305. So square root of 305, and then that's all over 2 times 1, which is just 2. So we get that, and that's about as close as we can get for an exact answer, but they want us to the nearest tenth, and so we're going to either go negative 7 plus the square root of 305, whatever that ugly number is, and all of that divided by 2. So we're either going to get 5.2, or, and then we can do the minus, negative 7 minus the square root of 305, and then divide that by 2, and we get, or negative 12.2. But this is geometry, so we get rid of that and accept 5.2 for our answer. We're not going to do a negative length on that one. All right, last one. LM is tangent to the circle. Find x, round to the nearest tenth. So we know LM is going to be times LM, so that's going to be 12 squared is equal to our full length, which is x plus x plus 2. So that actually ends up being 2x plus 2 if we add those together, times the external secant segment, which is another x. And so we've got one more of these where we're going to end up in a quadratic setting, but this one, we'll see how it turns out. So we distribute, we get 2x squared plus 2x is equal to 144. And so then we can subtract 144 from both sides, minus 144. And so we get 0 is equal to 2x squared plus 2x minus 144. You can actually simplify this a lot by dividing both sides by 2. So if I divide this side by 2 and divide that side by 2, I actually end up getting to reduce all these. So this ends up being just still 0 on the left. And then 2x squared over 2 is just x squared. 2x over 2 is, if we divide that by 2, we get just x. And then negative 144 over 2 gives us negative 72. And so this time we might try and factor this, try and think of two numbers that multiply to be negative 72 and add to be positive like 1 for this case. And it can actually be done in this case. It's 9 times 8 is 72. And so if you make the 8 negative, then it'll work out. So if I show this here, so we're going to do x plus 9, x minus 8. If we FOIL this together, we get x squared, and then outside and inside negative 8x and 9x combined to be just 1x, and then 9 times negative 8 is negative 72. So if those two multiply to be 0, one of them has to be 0, so either x plus 9 is 0 or x minus 8 is 0. So that leaves us to x is negative 9. Well, that's not going to work out, or x is 8. Turns out we really don't want this solution. We're doing geometry, so we don't care about the negatives. We want a real number, a real length, 8. So that can help us solve that problem.